Let's start with a reality almost every backend engineer has experienced. Nearly every server side application uses caching. We cache because recomputation is costly, slow, and wasteful. If a value has already been calculated once, it feels natural to store it and reuse it. At first glance, caching looks like an easy win, but once concurrency enters the picture, caching quietly becomes one of the hardest problem to get right. So instead of jumping straight to the perfect solution, let's walk through how a cache usually evolves in real systems. We begin with the most obvious first attempt. We create a simple interface task that represents a slow computation task. This keeps our design clean and lets us separate the computation logic from the caching logic. Now let's imagine a computation that takes time. For simplicity, this one just convert string into big integer. But in reality, this could be a database call, a remote API, or heavy CPU work. With this in place, the natural next step is to add a cache. Our first instinct is to use HashMap and protect it with the synchronization. This generic class with input I and output type O implements task interface, meaning it must override an execute method. The store a hash map here used as the cache. Keys are the input messages and values are the outputs. The actual task to execute if the result isn't cached. Here we wrap an existing task implementation, so you could pass the slow computation task and this wrapper will cache its results. Synchronized keyword ensures thread safety, meaning only one thread can run this method at a time, preventing race conditions on the cache. So first we check the cache. Store.get looks for cached result. If not found here, calls the underlying task dot execute method, stores the result in the cache using store.put, and we return either the cached value or a newly computed value. At first, this feels safe and correct. The hash map is protected and the logic is simple, but under load, this design collapses. Only one thread can execute the compute method at a time. If one thread is busy doing expensive work, every other thread waits, even if they want completely different values. Instead of scaling, the system queues threads and slows down. Suppose two threads call execute method at same time. Thread A enters execute first. Because the method is marked synchronized, thread A acquires the lock on the cache wrapper v1 instance. Thread B tries to enter execute method at the same time, but it blocks until thread A releases the lock. Thread A runs the method. It checks store.get. If the value is not cached, it calls task.execute and then put the result into the store. Finally, it returns the value and releases the lock. Thread B resumes. Now thread B acquires the lock and runs the same method. It checks the store again. If thread A already cached the result, thread B finds it immediately and skips the expensive computation. If thread A had a different input, thread B may still need to compute and cache its own result. All computations are sequential, that means zero concurrency. At this point, the intention was right, but the synchronization was too heavy. So the next improvement feels obvious. We replace HashMap with ConcurrentHashMap and remove method level synchronization. Here, store is a thread safe concurrent hash map used as the cache. So we check the cache, store.get method looks for cached result. If not found, calls the underlying task using task.execute, store the result in the cache using store.put, and return either cached value or newly computed value. Unlike V1 version, this version does not synchronize the whole method. Multiple threads can call execute method concurrently. Concurrent HashMap ensures safe concurrent reads and writes. This version scales much better. Multiple threads can now access the cache concurrently, but there is still a subtle issue. If two threads arrive at the same point and the value is missing, both threads compute the same expensive result. The program is still correct, but the cache has failed its core purpose. That is, duplicate computation is still happening. The real problem is that threads have no visibility into the work that is already in progress. They only see the computed results. What we really want is a way for one thread to say, I'm already computing this, and for others to wait instead of starting over. This is where the design changes fundamentally. Instead of caching values, we cache computation using future. So your store is a concurrent hash map where each input mapped to future. A future represents a computation that may be running or completed. So here again, we check the cache, look up the future for this input. If not found, we create a callable that wraps the task.execute method. We wrap it in a future task, a future that can be run. Put the future task into the map and start the computation by calling future task.run. Once this is done, thread calls future.get method. If computation is still running, this blocks until it finishes. If already done, it returns immediately. If computation is failed, it wraps the exception in a runtime exception. This version is a big leap forward. Now, when one thread start the execution, other threads wait for the same future instead of repeating the work. The waiting is efficient and the design scales far better than before. But there is still one tiny race condition left. Two threads can still sneak in at the same time, both checks the cache and creates a future task before either of one is stored. The window is small, but in concurrency, small windows matter. To close this final gap, we make the check and insert compound actions atomic using put if absent method. So we check the cache, look for future. If not found, create a callable wrapping task.execute method and then wrap it in future task. Try to insert it atomically with store.put if absent method. If another thread already inserted a future, use that instead. If not, create new one and then run the future task to start the computation. Post that, we call future.get. If computation is running, this blocks until it finishes. If it is already done, it returns immediately. And here is the important step. If task is cancelled, remove the entry and retry, since we are in infinite while loop. And if the execution failed, rethrow the underlying exception. Now we have something truly robust. Only one thread performs the computation. Other threads wait efficiently. Failures can be handled cleanly and scalability is preserved. Instead of locking threads, we coordinate work. Instead of protecting data, we manage ownership of computation. If you look back at this evolution, the lesson is very clear. Concurrency problems are rarely solved by adding more synchronization. They are solved by redesigning how work is shared. When threads cooperate instead of competing, systems scale naturally and predictably. This is the difference between writing concurrent code that merely works and designing concurrent systems that survive real production load. If you found this video helpful, please give it a thumbs up and subscribe for more technical content.